Today we're going to finish the chapter 18.2 notes. We're first going to talk about the standard reduction potential values. And so this is table 18.1. On page 709. And it looks like this table here. You will use this table on your tests. You will not get the activity series for your test. When you're looking at the table, it gives you the cell potential values for half reactions. The unit for these is volt, which we abbreviate with the V. A volt is defined as 1 joule of work per Coulomb charge transferred. Now, the standard conditions for these cell potentials: temperature of 25 degrees Celsius. For solutions, they are 1 molar solutions. And gases are at a pressure of 1 atmosphere. So, how did they come up with these cell potentials for metals? So, for example, in our model we used zinc and copper. So what they did is they compare to the standard. And so the standard is called She, which stands for Standard Hydrogen Electrode. And so if you look at the standard reduction potential chart, the values, hydrogen ions gain 2 electrons, forming hydrogen gas, and the cell potential is 0.00 volts. And so this was set up using a solution of 1 molar hydrochloric acid, and then hydrogen's a gas, so you have to have a metal in there as your electrode, and so that can either be platinum or graphite. So platinum's expensive, and so the more economical or cheaper electrode for this standard would be graphite. And so all the other metals are compared to the cell potential of the standard for hydrogen gas. And that's how they come up with the other values. If you look at the standard reduction potential table, the strongest oxidizers, oxidizing agents, these, if they're an oxidizing agent, they undergo reduction. Because they gain electrons. These are nonmetals. And so if you look at their position in the table, they're the highest in the table. They have the most positive values. The strongest reducing agents these undergo oxidation, which mean they lose electrons. They are metals, and they are the lowest in the table. They are the most negative. So what we need to talk about now is how to write line notation. Line notation is used to describe electrochemical cells. And so just like when we draw the voltaic cell, the anode components are on the left. The cathode components are on the right. And they're separated by double vertical lines. Those double lines indicating the salt bridge or semi-permeable membrane. And so the general form is the electrode, a single line, the ions in solution, double line to represent the semi-permeable membrane or salt bridge, ions in solution, electrode. And this side, the left side is the anode components, and the right side is the cathode components. So from our modeling activity, we had on the anode side, our electrode was solid zinc. The anode ions were zinc cations, separated by a semi-permeable membrane. There were copper cations, in solution, and then solid copper electrode. What we're going to do now is some practice on page 742, number 60. So answer the following questions using data from table 18.1, all under the standard conditions we talked about. So is hydrogen gas capable of reducing nickel 2 plus? So if hydrogen gas is capable of this, that would mean that the hydrogen gas is undergoing oxidation because it's the reducing agent, and nickel 2 plus would be undergoing reduction. So let's look on our table. So here is the reaction here for hydrogen gas, and for the nickel 2 plus, it's here. In order for this to be true, if nickel was undergoing reduction, it would have to be higher than hydrogen, and it is not higher. So for A, hydrogen is not capable of reducing nickel, so this is a no. For B, is iron 2 plus capable of reducing VO2 plus? So let's find, and we'll do this. B, we'll do, let's see, I'll color code them. A was in yellow, B will be in green. So is iron 2 plus capable of reducing? So let's look. So here's my iron 2 plus half cell reaction. Oh, let me fix this because I wanted to color code them. You can see that was A. B will do in green. There's our iron 2 plus. And then I'm looking for the, here we go, right here. Oh wait, that's not the right one. That is, oh sorry, it is. I just can't see my, yeah, that's a plus. Sorry, I needed to make that a little bigger so I could actually see what it was looking like. So this would be here. So if this is the case, then the iron will be undergoing oxidation, and the VO2 plus would be undergoing reduction, and it would have to be higher than the iron. And you can see that it is higher than the iron, so it is yes. Iron is capable of reducing VO2 plus. For C, we're looking at iron 2 plus. So we're looking at this one again. Is iron 2 plus capable of reducing Cr3 plus to Cr2 minus? Cr3 plus to Cr2 plus, sorry. So that would be here. In order for this to happen, then the iron would have to be undergoing oxidation to be the reducing agent. The chromate would have to be undergoing reduction. It would have to be higher in the table. It is not higher, so the answer to this is a no. So here's your homework, which is due Monday. Along with that silver problem you had to do, you need to do page 742, number 37A, 39, 43, 57, and 59. You're not going to submit it online, you're just going to do it on a sheet of paper, bring it in, and I'll check it when I check the silver problem from the modeling packet. If you have any questions or concerns, please send me a message in Schoology.